Hi, everyone. Thanks for coming to my presentation titled Evaluating Urban Heat Risk Through Coupled Detection and Indoor Overheating Analysis. This is current work that's being carried out under my PhD work at MIT in the Building Technology group in the architecture program. So first, to introduce the topic, as we all know, global temperature increases have been a new norm, of course. And for instance, this past July, was confirmed as the hottest month on record. But coupled with that, this is extreme weather events we'll explore, and what we're seeing here is, of course, there's a lot more frequent heat events as well, which is what this work is focusing on. And for instance, 92% of recorded extreme weather events were within the past decade. And the number of cities exposed to extreme temperatures will nearly triple by 2050. But of course, it gets a lot more complicated when we turn our attention to cities. When we want to capture what kind of vulnerability will be expected, of course, the effects are not going to be experienced equally. It's estimated that around 620 cities, more than today, by the year 2050, will be having heat exposure. And this is a matrix essentially that's looking at a few global cities, and where vulnerability is likely to happen most would be in areas where there's going to be higher increases in temperatures, but also lower cooling adoption. That's related to, of course, demographic data. So it quickly becomes very convoluted, but it is very important to represent in the studies that we're carrying out these days. So this is just an example of higher vulnerability cities. And sort of this is the main thesis of the work. It's, with this climate imperative, it's important to understand the magnitude of heat risk that's going to be experienced. So when we talk about magnitude, it's important, of course, to quantify the severity of the weather intensity that's likely to occur for a particular city, but also be able to assess it at the scale of the city. So understand what simulation methods we need to employ to capture city heat exposure, and more specifically on the building stock. So looking at the indoor level vulnerability that's likely to occur, we want to represent the building stock accurately. So looking at how we can accurately collect data from each each city's building stock. So this is sort of the broad areas of research that I've been working on, starting from extreme climate representation, and this is where I'm working on constructing representative peak year weather files that are being inputted in our simulations. But today, the work that I'll be sharing is more in steps 2 and 3, which is urban building feature detection. So the goal and the contribution of this work is deploying computer vision methods to extract more detailed facade characteristics. So in this example, I'll be showing window coverage for accurate digital twin representation of the building stock in the city. And then step 3 is indoor overheating evaluation. So being able to couple that detected data into our simulation models to evaluate indoor heat exposure. And this is sort of where we're going to arrive to at the end, which is the ultimate goal is urban heat mapping on the indoor level and asking the questions, what do cities need to know to inform heat alleviation in cities? And really, we want to start asking deeper questions such as, how do we communicate and visualize risk within a city? How can we better localize risk in urban environments with, again, more specificity to the building stock? And what are the time spans and spatial scales we should be incorporating in our analysis? And ultimately, how can we improve the accuracy of these models for better actionability and reliability to communicate to cities? So this is just a map showing annual overheating hours per building in a sample neighborhood. And again, just to dig into that a little bit more, it's really about tying the spatial resolution. So are we looking at a city level, or are we looking at a building, or ultimately also being able to localize it to a floor level? How can we get more intricate insight on that and data? And then looking at simulation models. So not just looking at isolated building by building level, but looking at what the urban heat island condition would be at in every specific neighborhood. And ultimately, the highlighted goal at the end is to be able to have some form of understanding what the exposure and intensity of heat metrics is going to look like in these cities. And just from a kind of broader drivers of overheating risk drivers in cities, we sort of know that location and climate, envelope characteristics, orientation, exposure, of course, floor level and occupancy are key drivers. But then on one question that's this research focuses on is windows are usually unknown and assumptions need to be made, and of course they control a lot of the heat exchanges that are happening with the outside and the indoor environment. But they're also connected to orientation and ventilation as well, and so they have a high influence and are typically difficult to obtain because cities don't typically collect them. Which brings me to the start of the urban feature extraction work. So the central question is what building features can we extract to enhance the resolution of building performance models. And computer vision methods have been widely deployed to investigate this question, and they've been centered on multiple methods from pixel labeling and rule-based approaches to machine learning approaches that are centered on utilizing CNN's convolutional neural networks to extract this data from visual imagery. But we can broadly categorize them into grammar-based and learning-based methods. So what this research does is really, we ultimately want to arrive at this, is that we want to look at, automate the extraction of building facades and know what the window to wall ratios are, which is the coverage of windows to solid area of a building, essentially. And the challenges are, again, that in the absence of this data, mainly assumptions need to be made. So then we end up misrepresenting what indoor environmental performance could look like. This is sort of our broader methodology for this work. We first automate the image sourcing and operations of going from geodata frames and using GIS data, and then looking at facade identification, but only looking at the areas of the facade we want to calculate information from. We deploy two models under the classes that I introduced, grammar-based. So grammar-based is essentially just looking at how we can extract rules or patterns from a particular building facade. So that's not reliant on training data. And then the CNN-based method is reliant on collecting data from the built environment and imagery, essentially to locate these windows. And data evaluation is carried out in comparison to manual measurements, but also we ask deeper questions such as, what resolution are we really getting? Is the algorithm robust enough against variations that you see in typical design conditions? And this is the CNN-based workflow, again, going from image extraction. So we're going to be deploying this model in Lisbon as a case study, and looking at building polygons, and then going and automating camera locations as well. And then essentially arriving using Street View imagery to collect an image by image representation of each building. And then finally, we compare the outputs, the accuracy of the two outputs based on the grammar-based and the convolutional neural network methods. And the CNN-based method gives us an accuracy boost. It's more generalizable. It's based on around 4,000 images of training data in different cities, so it can adapt more and be applied to different contexts. Whereas the rule-based method is generally more rigid to different design conditions. And we also look at comparing the performance of the methods in terms of error distributions of different building heights and different building ages as well. And this is where we see, for the most part, the CNN method is behaving better, but there's a slight improvement in the grammar-based method where it behaves better with windows that are generally bigger. And these are the two outputs of the two methods and what they generally look like. And depending on the different strengths and weaknesses of the different design condition, we come up with a hybrid method that fuses them both essentially to arrive at higher detection accuracy. But then utilizing the CNN method, we can also go beyond just window detection. We can go towards calculating 5 additional metrics. So window sizes, for instance, of the top floor, location of largest windows, and window aspect ratios and total building height estimation. Again, to more accurately represent digital twin in cities. This is what it looks like, for instance. And then finally, we get to the overheating risk mapping portion. So essentially, looking at geometric data. So for instance, one geometric piece of information that we now have is window to wall ratios on the building level, on the floor level as well. And then looking at building templates, building archetypes, weather data, and other information we can also collect from non-geometric sources. And then essentially carrying out some form of thermal simulations to calculate output metrics that tell us how the indoor environment is behaving. And the simulation method tries to incorporate urban heat island approximations as well as indoor overheating analysis. So with the urban heat island, we can have outputs that have morphed weather files related to the density, for instance, in the built-up area, essentially. And the internal approximations look at carrying out essentially simulations to look at how often, what temperatures look like on the inside of the building, and calculating overheating hours. We just calculate exceedance hours that go above 26 degrees in this condition, but other metrics can be used. Finally, this is just the approximation of the blocks we use to represent the Lisbon analysis area with the different orientations and the different window to wall ratios that we've now measured. And just going, we can look at data representation as well. This is looking at sensitivity of heights and window to wall ratios to different urban canyon widths and orientations as well. We can calculate where the maximum conditions are likely to occur. So for instance, intuitively we know, for instance, that higher exposure areas are at the top floor with larger window to wall ratios with southern orientations. And as opposed to that, more shaded conditions and lower levels have lower overheating hours. Finally, we have an assignment logic that looks at getting that window to wall ratio information, other information we know on building constructions as well. And we assign essentially these conditions to the context that we're analyzing. And the goal here is to have some form of urban heat mapping representation where we can actually, within a specific neighborhood, calculate and categorize the overheating conditions that are likely to occur. So now we just discretized it from 0 to 400 hour annual buckets of exceedance hours, and we map them. But essentially, we can go towards doing the same exercise for different parts of the cities as well, and then categorizing where those higher peak conditions are likely to occur within the analysis area. We can also use future weather files to calculate the highest overheating potential areas in the future. So this is, for instance, using the 2080 morphed weather file. And we can identify where worst conditions are. For instance, here, worst conditions we can see are in older construction residential units. And then finally, to reflect on what this means and how we can use it is, we find that the largest growing annual overheating categories within 1,200 to 16 hours. And I'm at time, so I'll wrap this up. We're currently also working on enhancing our detection workflows to more intricately represent more and detect more features from the building stock as well. And then finally, also looking at merging the extreme projections within the simulation workflow. Thank you.
Thank you so much, Nana. Any questions from the audience? Can you maybe, I'll just share.
Thanks for a very interesting study. I have two questions. Mm-hmm. One question is about key methodology that you consider the interaction between the building and the environment. So I didn't feel that work. Second, I'm thinking of using art. So I'm just wondering about how you extend from one single building that you generate about the neighborhood.
So I'll answer the second question first. I remember the first one. So yes, we consider, so in the parametric model that I run, we know that I extract knowledge and measurements from the context within the specific neighborhood that was being analyzed in Lisbon. So I know everything about, maximum, minimum, average urban canyon widths. I know from the measurements what the window to wall ratio percentages were, what the averages were. This is something important to know. This is only for residential applications. So I know I've extracted this information, and I'm using a local weather file as well that's generated specifically for Lisbon. Some assumptions have been made, of course, related to vegetation cover, heat generated in the context. Of course, these approximations can be changed, and then I use those approximations to then calculate different levels of morphed weather files that are basically urban weather generated files related to those local conditions. The second question was how I go from urban to building.
Yes, how do you consider interactions?
Okay.
Because you're interested in indoor or outdoor.
Yeah, so they're basically, once I have that morphed weather file that's generated, that's represented the urban heat island effect based on these assumptions and whether they're measurements or things that I know from the GIS data set that I also have, I then use that weather file to input it within my simulation, and I have those same geometric relationships represented in my simulation as well. So I'm using a combination. For the morphed weather files for the urban heat island effect is the urban weather generator, For the indoor thermal conditions, it's a workflow that has 3 different simulations. So for the CFD, I'm using EDDI. For the internal temperature approximations, it's essentially Energy Plus that's running on Climate Studio.
Thank you. There was another question that we're running out of time. If you could connect with the speaker after the. Oh, it was the same question. Perfect. Thank you.